The beginning of these notes use another video, so please go back to Canvas and get the link for the solubility introduction. Please jump to slide 6 in your notes for the rest of this video. Here we have the dissociation of NaCl, and you can see that Na plus ions are the gray ions, and water, the purple and green molecules, are orienting themselves so that the water portion, the purple part, is facing towards the sodium positive ion. And that means that the attraction between the slightly negative oxygen side is going to be attracted to that positive Na plus ion. The same thing is going on with the chlorine ion. So we have the big green dots there in the middle with the water molecules, and you'll notice that the blue dots, or the tealish dots, are the hydrogens. That's the slightly positive side of the water. And they've oriented themselves so that water's slightly positive side is near the negative chloride ion. This, where water kind of works its way in between the Na plus and the Cl minus, this is what gives us that dissociation, or the breaking apart of our ionic compounds. So here we have some examples of what happens to different compounds when we put them into water. So like we said before, ionic compounds are going to dissociate completely. So we have NaNO3, the Na plus ion and the NO3 minus ion are going to be broken apart from each other. And we indicate this with an aqueous symbol. Whereas before, on the reactant side of our equation, we have it in a solid form, represented with an S. Now, when we have polar covalent compounds, they too will break apart when they get put in water, but instead of breaking the molecule apart into the individual little pieces like we did in the ionic compound, we are going to just break the molecules apart from each other. So we have this CH3OH as a liquid form. When we put it into water, the CH3OH is going to stay as one compound. We just have the compounds breaking apart from each other. So we still call it aqueous. Acids are a little bit more tricky because some of them want to break apart completely, and other ones, there's this really good positive-negative attraction, or we might actually be participating in a little bit more of a take-take relationship than other acids, so we don't get that full, complete breaking apart. So strong electrolytes like we have here with H2SO4, the HSO4 portion really could care less about this H. That the SO4 is really going to suck those electrons in pretty tightly. So it kind of leaves this area of H to be pulled off, especially if that negative side of the water comes nearby. With the negative side of the water, it is going to really grab a hold of that H plus ion and rip it off and become a hydronium ion. With our weak electrolytes, the fluorine that we have down here wants electrons, but doesn't have quite the pulling force as, say, our SO4 polyatomic ion. So it's not going to pull that electron as hard from the hydrogen. So because of this, the hydrogen and fluorine relationship is not really a give-take like we saw with the stronger electrolytes of the SO4, we're really going to see a little bit more of a take-take relationship. So that makes it slightly more of a molecular, like a very polarized molecular compound, and the water is not going to be able to break that part. Okay, so we've always heard this term like electrolytes, and I know like in sports we want to drink electrolytes, and Gatorade and Powerade and all of these other drinks are really trying to like push the electrolytes, and we really don't know what those mean. It's just a fancy term. We've been covering electrolytes for a while. Electrolytes are just ions that have been put in water, and we know that they make water conductive. So ionic compounds would have electrolytes that they dissolve completely, whereas molecular compounds would not be electrolytes. They don't dissolve together. So when regular Gatorade, if you just get Gatorade, it's got a lot of sugar. Well, sugar is a molecular compound. It's not really going to help your body out like the electrolytes can. When you sweat, you lose electrolytes. You lose sodium and chlorine, and you need to replace those. You also lose potassium. So when you're replacing it with sugary drinks like regular Gatorade or sodas, you're not really getting those electrolytes back. G2 Gatorade, which is Gatorade's less sugar version, has upped the electrolytes. So they put more sodium and chlorine and potassium and those things back into the Gatorade, but they also lessen the sugar so that you're getting a little bit more of those electrolytes. And our body needs those electrolytes because having those conductive, those ions that can move, helps our body send those electrical pulses to our muscles to make them work better, as if we're doing show choir or baseball or whatever we're looking at. We want to be in control of our body, so we need to drink those electrolytes. And like we said on the previous page, strong electrolytes, ones that really have those ionic type bonding, they're going to dissociate completely. And then the weak electrolytes, those like the hydrogen and the fluorine, they're not going to separate as much, so we're not going to get quite a bit of conductivity through those. So when we're looking at the strong and weak, we're going to talk about solubility, or the ability for it to loosen and break apart. Here we have kind of just some general rules. I just put back in here the strong electrolytes completely break apart, the weak ones don't. So usually we're talking about being soluble in water because water's pretty cheap and it's pretty easy to get compounds to break apart in for the most part. So water-soluble things, anything like Cl-, Br, so chlorine, bromine, iodine, all of the ammonias are going to do it. Most of the metals, or all of your metals from the first column, anything with acetate, C2H3O2, all of your NO3 minuses, all of your ClO4s, and all of your SO4 minus 2. Now we do have some exceptions. So when you're looking at chlorine, bromine, and iodine, we have things that are insoluble in water. So these pieces over here, Ag+, so silver, lead, and mercury, are not going to be soluble in water. It doesn't matter what pieces you put them with, they are not going to be soluble with the water. O, oxygen just tends to not be dissolvable in water. Same with sulfur-based things. Phosphates, the PO4 minus 3, most of those are going to be insoluble. If they're paired with like those first column metals, we'll get phosphate to dissolve because those first column metals really want to give off those electrons, so they become polarized. But anything else, like with the two, giving anything from the second column giving two things off, or two electrons, they just really, the PO4 just does not pull that hard. Same thing with our OH minus. Again, if it's with something with the first column, it's really, really, really going to pull those away. Those metals really want to give off. So our OH minus is going to be dissolvable in water. but with anything else, it's going to be insoluble. And then again, we have our SO4s are normally soluble in water unless we're with that lead, and in this case also barium and strontium. So SO4, when it pairs up with barium and strontium and lead, really kind of latch on pretty tightly, and they won't break apart when they get into water. So this solubility idea we are going to take and put into our reactions and be able to predict if we are going to produce a solid or if we're just going to have mix two clear solutions and make a clear solution. So this solubility information is really key to us when we're looking at what our reactants are and our potential products. If our potential products are water soluble, they're probably not going to form. They're going to stay in aqueous. It would just be like we picked them up and put them straight into water. If we mix things together and they make an insoluble compound, that's when we're going to get the yellow or the white chalky stuff or whatever that is. We will have that fall out of solution as a precipitate.